Okay, so how is everyone today? Okay. So, a couple of announcements. So, you've probably noticed that the homework has been delayed. Well, sorry for that. Though the last class was found it to be perfectly acceptable. So what we're going to do is that the ones that were delayed, they're still going to be posted, and they're going to be due in a relatively short turnaround, but they're all going to be for bonus. So should you choose to do them, you couldn't possibly injure yourself. Okay, then now that things are back on track, the homework schedule will continue normally. Okay, so any questions about any of that? Well, I'll post the announcements today, this afternoon, and it should be clear. Yes?
This week's quiz involves which odd numbers, like 0, 7.
Oh man, I don't know. Yeah, I think 7 and 8. That sounds right.
So last week's.
Yes. Okay. So last time we were talking about linear models. So let's do that a little more. So today's the 18th. Okay. So here's an example. Suppose that we have a town with a population which grows linearly. That is to say, if you were to plot the population of this town over time, it'd be a line. Fine. Suppose that in year 1314, the population was, I don't know, how about 1,000? Was 1,000, and in year 2017, the population is how about 40,000? Okay, so we've got such a town. First request is to construct a linear model. So find a linear model. Okay. So the first, pardon me, the first order of business is to give names to the kinds of symbols that, to the kinds of quantities that we're dealing with. So we've got two kinds of things here. We've got these numbers, which are years, and we've got those kind of numbers, which are people, persons. So what symbol do you want to use to represent years? X for year. Okay. And then what do you want to use to represent population? Okay, I'm gonna veto Y because that might sound like a year. A Q? A capital Q? Okay. So this is gonna be, because obviously Q. This will be population. So what do we have about this line? Like what knowledge do we have about it? 2 points. So you're saying that we have 2 points on the line. What's one of the points? So one of the points, x1, q1, is equal to what?
X2, Q2.
Okay, not quite. So what I want is this, the specific.
13, 14.
Okay, good. 13, 14. And then comma 1000. So what that's saying is that in the year 1314, the population was 1000. Okay. But we also have another point, x2, x2, q2. So what point is that?
2017.
Very good. So we have 2 points. 2 points. And then what's that formula for a line? What's the name of it? The point slope formula, right? So notably, its name is not the point formula. Right. So what are we lacking? A slope. So the first order of business is to find a slope. Okay, so then delta x, change in x, that'd be x2 minus x1, which would be 2017 minus 1314. 703. Okay. So that's the change in x. So that's saying that we're tracking business over the course of 703 years. And then delta q, well, that'd be q2 minus q1, which is 40,000 minus 1,000, and that's surely 39,000. Very good. So over the course of this 703 years, the population went up 39,000. So what's the slope then in terms of these two things? In terms of these symbols? Very good. It would be delta Q divided by delta X, which is 39,000 divided by 703. Okay. Any question about finding the slope? So, now we can use the point slope form of the line. Copying it from memory, it's y minus y1 is m x minus x1, but now we need to do a little bit of translation from the way we wrote down the formula originally to the symbols that are in the story now. So this one has x's and y's, but our story has x's and q's, so which one is which? Are x's really x's, or are they actually y's? And what about the q's?
The Q's are X's.
Are they?
Yeah.
Well, let's think about it. Let's think about it, because the other thing, another thing, is that in the point slope formula, so now I'm going to draw a box where this is back in the day, and by that I mean last week. So this is back in the day, and then what was delta m in those, or sorry, what was m in those times? Rise over run, which was delta y over delta x. So this is back in the day. So comparing this slope delta y over delta x to what we currently have, are x's x's or are x's q's? X's are x's, right? Because they're both in the denominator. And the y's are playing the role, a q is playing the role of y. Okay. So we'd have q minus q1 is m times x minus x1, so that q minus 1,000 is 39,000 over 703 multiplied by x minus 1314. Okay, then on such exercises, I'm always going to request for you to solve for the output variable. That is to say, for q in this exercise. So let's solve for q. So multiplying out the right-hand side, $39,000 over 703 x, and then minus, I'll multiply those two together. $39,000 times 1314. So that would be 512, and then 46, and 4 zeros, and then over 703. Okay, good. So now I'll move the 1,000 to the other side. So q is 39,000 over 703 x minus 512, 46, 4 zeros over 703, and then plus 1,000. So how do we combine these two into a single number? Find a common denominator. So we could, this one has denominator 703. What does this one have denominator? 1, right? So we could multiply this one by over 703, right? So doing, that gives us 39,000 over 703 x, then minus 512, 46, 4 zeros over 703, and then plus 703 with 3 zeros over 703. And then I'll type that in. Well, this is part of the point, that when you're modeling things, you know, it's nice when I give you the exercises and it turns out that the equation is y is 3x plus 4. Nice, okay? It doesn't happen when you're actually doing this. Okay? So 39,000 divided by 703 x, and then minus 505 43 with 4 zeros over 703. Okay, so now you might look at that and say, that looks a little bit crazy. And you wouldn't be that far off the mark. How could you confirm or deny that you've done this properly? You mean plot it?
Yes.
Okay, plotting it would help, but suppose this is off the table. What could you do?
Plug in the x, plug in more numbers, it comes out equal.
Right. Because how did we obtain this line? We obtained this line from this data.
Yeah.
So if we plug in year 1314, what population should we determine? 1,000. Well, let's check that. We'll check with the point x1, q1. So the question is, if we substitute 1,000 for q and 1314 for x, is the equation true? Well, that sounds like a job for the calculator. Okay, a moment of truth. It should be 1,000. Oh wait, I got 10,000. What went wrong?
I don't think that. Too many zeros in there. Yeah, 390.
Oh, I did 390,000. Okay.
Close enough.
Yeah, it's close enough. You know, what's an order of 10 between friends? I put too many zeros somewhere else too, probably. Just a sec. Okay, either that or I made an error. 505.
Pretty sure the syntax is just confused.
Yeah.
Nah. Minus 50543 and then over 703. I'm not getting it. So I made an error somewhere. Which one? But it has 4 right there. But there's only supposed to be, but there's not supposed to be that many. Okay, good. So this is fine. This is fine. Because remember, the whole point was to confirm or deny whether or not we did it right. So evidently what I have written on the page is not right. So that's good. That's good. Now let's find where it went wrong. And now what you're going to wonder is, did I plan it or did I not? I didn't. I didn't. This is entirely accidental. Yeah. Yeah, this is all planned. Okay. Where did it go wrong? 39,000 times 1314.
Oh, she was right. You know, the 51246.
Look, yep. That number has 3 zeros.
Not one.
Ha. And then when I made that was the first mistake, and then the second mistake when I added the other 0 in the other place. Almost had offsetting mistakes. Okay, good. Well, that's why you got to know how to check your work. Okay, so this one is just wrong, so I got to replace that. Replace that. Okay.
So how did we get 10,000 earlier?
The answer should have been 1,000.
Right.
But the way
Just because you had a 0 on the extra 39.
Yes.
because I had an extra 0 here, and then I accidentally put another extra 0 on this one, and that's just like multiplying both of them by 10.
Okay.
Okay. So it'll work out. Let me just see. Oh no, I gotta fix that number.
The number was correct, except for 1, 2.
Okay. Okay, I was just off by 1 0. Okay. So now my new number is 50543 and then 3 zeros. Okay. Okay. So now plug that one in. Okay. So here's the moment of truth for the second time. Okay, we did it.
Good job.
Now we know that it goes through one point, but does it go through the other one?
There's only one way to find out.
There is.
Flip them around.
Let's do it. So what should the left-hand side be?
40,000.
40,000 equal. Okay, this one will be easier because I already have it almost typed. Okay, so now I'm going to plug in 2017 and we should get 40,000. Okay, incredible. So, sorry? I don't know, but it's called a TI-30.
No, it's just got a good comment.
Oh, I don't know. I don't have any idea. Okay. So that's good. So now you'll never forget. Oh yeah, I remember that time instructor made a mistake, but was able to catch it, right? Was able to catch it because I knew to plug in and check. Okay. So fine. Next question. So that was question 1. Question 2 is about the same linear model. The question is what was the population in year 1800? So that's a question in English, but could someone please translate it into algebra?
Q equals 39,000 over 703 times 1,800 minus 505.330 over 703.
Okay, good. So to say it slightly briefer, I'll say what I'm asking for is please tell me Q when X is 1,800. Okay, so I'm going to type that into my calculator. I'll write it down first. So 39,000 over 703 times 1,800 minus this crazy number. Okay, so now I'm going to write something down, and it's not going to be correct. So, but I want to ask, it's going to be correct in a way that is not a little bit incorrect, but unacceptably incorrect.
Oh, there's an acceptable level of incorrectness.
Sure there is.
I feel like this scale.
So how about this? Okay, so suppose I fumbled the calculator and wrote down this number. So in the first place, this isn't the correct number, but this number is incorrect in a completely unacceptable way. So because it's conceptually wrong. What's wrong with this?
Too big.
I agree, but lots of
Come on.
I agree.
Space in between.
Oh, yeah, it's a gap.
A gap.
Oh, I put the gap there because I don't like putting commas.
Gotcha. Doesn't have a
It's not constant.
Okay, so 51,000. What's wrong with 51,000? Okay. But there's something wrong about how big 51,000 is.
It's
Too
greater
big than when in 2017, so I don't know.
and it's a positive linear model.
Right. So let's think about this. The time, the place, the points in time that we know a point in time at 1314 at that year, and we know another point in time at 2017. And where did we just ask about?
Right in the middle.
Yeah, we asked in the middle-ish. You know, kind of right here is at 1800. So in year 1314, and the population is growing linearly. At year 1314, the population was 1,000, and the population here is 40,000.
Right.
If I ask you for an intermediate time, then you had better give me an intermediate population. That is to say, this is wrong because it's not between what two values?
1,000 and 40,000.
It's not between 1,000 and 40,000. Okay? So that's what I meant when I said it's wrong, but it's categorically wrong. So to write this down and to submit this as the answer is to fundamentally misunderstand what you're doing. Okay? Yes?
I mean, I'm assuming we'll just get these shows right.
Yeah, I'm going to do, well, yeah, I haven't typed it in yet. Okay, so then my calculator rounding to the nearest individual. So this one, we talked about this one, so not that one, rather this one. 27,961. Okay, now is that value intermediate?
Yes.
Yeah. Okay. So that passes the reasonableness test anyway. Okay, good. How about 3? When will the population be 50,000? Okay, so now, by analogy to this sentence that I'm boxing in blue, what is the analogous thing that I'm asking for this one?
Find y, find Q when Q equals 3,000.
Yeah. So here, subject and object, what I'm doing is I'm switching their positions. This one was find Q when X is 1800. This one is find X when Q is some other value. So find X when Q is 50,000. So now before we even answer the question, we're going to, but before we even answer it, we have 2 points in time where we have measurements. 1314 at time 1314 and at time 2017. Now you should be able to tell me, have the time is split up into 3 regions, the left region, the middle region, and the right region. You should be able to tell me right now, in which region will we find X?
Right region.
The rightmost region. It surely must be there. Why must X surely be in the rightmost region? Because here at this right point, the population is 40,000, and we're asking about when it's 50. So surely it's over here in the right. So if you were to respond with an answer that wasn't in the right region, then it would be wrong, but not a little wrong. It would just be utterly wrong. Okay? Okay. So let's do it. Find X when Q is that. So 50,000 is 39,000 over 703 X, which is what we're looking for, minus 50543 with 3 zeros over 703. Okay, so supposing we want to solve for X, what do we do? Okay, add the thing to the other side. Okay, 50,000 plus 50543 with 3 zeros over 703 is 39,000. 703x. Okay. Now what? What do you think? There's lots of ways to go. Okay, multiply both sides of the equation by 703. I like it. Why is that a good thing to do? Okay, so if we were to do that, then there'd be no more denominators and no more fractions. I like it. Let's do that. So 703 multiplied by 50,000 plus 50543, 3 zeros over 703 is 703, 39,000 over 703. I'm just writing this for the benefit of folks who are less confident. Do you observe that on the right-hand side the 703s would cancel? And you would have 39,000 x's. Then when you distribute this to the 50,000, that's just multiplication. But when you distribute the 703 to this fraction, what happens? The 703s cancel. Okay, so 703 times 50,000. $3,515 with 4 zeros, and then plus 50543 with 3 zeros. Okay. 8569. 3 with 3 zeros is this much x. Okay, divide 85693,000 over 39,000 is x. Okay, so now it's not clear to me yet whether or not this is reasonable, but let's type that into the calculator and see. Is that a reasonable number? 8569 3000 divided by 39,000. Okay, so then this is saying, rounding to the nearest year, 2197. So would someone please interpret that number for us? What does that mean? In the year 2197. Very good. So is that in the correct part of the timeline?
Yes.
Yeah.
Yes. Good. Any questions about this kind of thing? Yes?
About dealing with actual population charts that fluctuate in order to extrapolate that.
Uh-huh. I'm listening.
How would you apply the different formula in that situation? Because it's not exactly linear.
Okay, so a couple comments. And the first comment is that no population that I am aware of grows linearly. They are all curvy. The reason is because populations, at least when nothing's killing them, and when they're growing in proportion to their current size. So that's why this year there's 2 rabbits, next year there's 20 rabbits, and then the next year you're completely overrun by rabbits. Okay. So they just don't grow linearly. This is the first objection. The second objection, yeah, logistic is the right math word. Then the other thing is that you might say, well, I have a lot of data and I want a linear fit. That's a different matter. If you just want to look it up, the phrase to look up is called least squares, for reasons that I'm just not going to go into it. Well, I'll be glad to talk to you after class about it. That'd be fine. Okay, next topic. So this is section 2.4. It's called complex numbers. Now in the English language, complex, the word complex has at least two distinct meanings. One of them is difficulty. Like you could say, oh, this is really complex. It's a really complex math problem or whatever. So that means like elevated difficulty. But there is another meaning that's not that meaning. And an example of its usage is a shopping complex, right? Which is not a region in which it is particularly difficult to shop. Okay, that's not what a shopping complex is. Rather, what is a shopping complex?
Place where it's easy to shop with a lot of different shops.
There you go. So in this case, complex means consisting of more than one part. Okay? So that's what we're talking about. So numbers with more than one part. Okay, so here's an equation. X squared minus 1 equal to 0. Nice equation there. I'm going to solve it with radicals. That is to say, I'm going to move the 1 to the other side. I'm going to compute radicals of both sides. Okay, so what is the square root of 1? 1. And what is the square root of x squared? Not x. The absolute value of x. What x's could you put inside of that absolute value so that 1 would come out? 1 would work. Negative 1 would also work. Okay. So that's a nice equation. Okay. What if we make a slight modification and I change the equation to this? So what's the distinction between these two? Right. That one change. So if I follow the same pattern, then I would next write x squared is negative 1, which surely is a problem, right? Because no real is going to square to negative 1, right? A positive real wouldn't do it, because if you squared a positive, you'd get a positive number. 0 won't work, because 0 squared is in fact 0. And a negative real wouldn't work, because if you square a negative, then you get something that's positive. So you know, you might say, okay, well, we just can't do that. Okay, but now I insist. I insist. We're going to do it. Okay, so what we're going to do is the following. I'm going to say that no real x can do this. So we'll define the unit imaginary number. So what we'll do is we will define the quantity that we will denote with little I. So define little I to satisfy the equation x squared plus 1 is 0. So notably that means about I that I is not real. But don't misunderstand that adjective. That doesn't mean that I doesn't exist. It just means that it doesn't belong to the set that we're calling the reals. It's still a thing. So immediate consequences of this are that what is I squared is negative 1. You square I, you get negative 1. Okay, what if you square negative I? Well, the negative would square away, right? The negative would square away, and you'd be left with I squared. But what's I squared?
1.
What is I squared?
Negative 1.
Negative 1. So I squares to negative 1, and so does negative I. They both square to negative 1. And we will define the following, that the square root of negative 1 is now I. Interesting. So as a result, before today's class, it would have been fine for me to prompt you with this. What would be the correct response? 5. And before today's class, if I were to prompt you with this, what would be the correct response before today's class? The correct response would be to say that this is undefined. Okay. However, we can write this now as, say, negative 1 times 25. And how can the 25 come out of the radical? As a 5, right? It can come out as a 5. And then, what's the square root of negative 1? It's I. Interesting. So the square root of negative 25 is 5i. Okay. What if I were to ask, what is the square root of negative 27? So how much can come out? So an I can come out, right? I think we can agree on that much. So 27 and then I. One notable thing is that when I write things to the right side of a radical, to make it clear that the thing is not in the radical, I put a little hat. Party hat on the radical right there, because when you write or see something like this, it can be a little bit unclear. Is that X in there, and they just didn't extend the house far enough, or is it out? I don't know. It's not clear. But if I change it to this, okay, the X is outside. So what can we do with the 27? We can take a 3 out, and then what remains inside? A 3. Okay, good. Any question about this? Yes, that would be just fine for you to write it as 3i square root 3. That's fine. Okay. So, remark, complex numbers. The set of all expressions of the form a plus bi, so the set of all of those where A and B are real. So both A is a real number and B is a real number. So the set of all such things is called the complex numbers. And just like the reals are denoted with fancy R, the complex numbers are denoted with fancy C. See, with a little extra bracket or whatever there. A plus BI. So this part, the A, this is referred to as the real part. And the B is referred to as the imaginary part. So I could say, for example, what is the imaginary part of 3 plus 4i? So what's the imaginary part? Just 4. Just 4. There's 4 i's. So the imaginary part is 4. Okay. So, now here I want to let you know that every time that I say real numbers, I laugh inside. I laugh inside because back in the day, there were physicists and scientists and mathematicians, but they were all actually the same people. There weren't those names yet. And at that time, all such folks were called natural philosophers. So, like Isaac Newton, famous guy, he was not a scientist or a mathematician or a physicist. He was a natural philosopher. It's only through the lens of history that we refer to him as such. So folks who would eventually become mathematicians are the ones who said, you know what, I want to think about this. And the folks who would eventually become physicists said, no, that's ridiculous. And more or less said, that's just a figment of your imagination, which is why these are called imaginary numbers. Okay, then the mathematician folks, because they're the ones doing the math, they're the ones that got to name the other things. So retroactively, the set of numbers became the real numbers as sort of a backhanded joke. Okay, so so that's funny. But in the end, the mathematicians are the ones who got the last laugh because the jewel of all physics is quantum mechanics. And what set of numbers does quantum mechanics occur in?
Imaginary number.
The complex numbers. What imaginaries all over. So every time I see a physicist, I like to say something like, you know what we use imaginary numbers for? Counting our unicorns. And quantum mechanics, don't we? No, I like physicists. Okay, have a nice Monday.